Hello, we'll get started very quickly. For those of you who don't know me, I'm Andrew. I work for XenServer. We're now part of Cloud Software Group. It's all a little bit complicated. The name of this presentation comes from a saying of a friend of mine I met during the speculative work. Basically, getting irritated at the fact that every single time we have an argument, we find yet another case where things don't work terribly nicely. He has decided that sharing is now mutually exclusive with security. I will let you judge by the end of the presentation, so let's get started. For those of you who did read my abstract and had chuckle at the end, yes, one of the big problems we've got now with CPUs is that they are so complicated, the architects cannot reason about them. So, we care about protecting users. Otherwise, what are we doing? This has been work for 6 years. It's still going. There are still problems. And the reason we care this much is not because everyone in the world is running speculative attacks day in and day out. It's because a speculative attack can silently leak data with no trace that it happened. And some of the things that people are going after are TLS private keys of a web server or a service. It's a couple of hundred bytes, a couple of thousand bytes. You can easily spend a month doing a low-level attack if you end up getting star.google.com as the secret you extract. So this is why we place such the risk is astronomical, even if the likelihood is low. On top of that, we have cases a couple of times a year where you get another 10% performance hit, and yeah, no one likes a performance hit, but when you're the size of a cloud, that's another 10 data centers. Actually, one of the people who reviewed this earlier said I should change that 10 for a 50, and I'm pretty sure he was not joking. It's a big problem. Stuff is getting more complicated, and we do now see speculative attacks in malware. They're still a little bit primitive, but they're there, they exist, they're a problem. The other important thing to say is that the hardware vendors are learning at the same rate as we are, seeing as it was a completely brand new problem, and yes, it shows. 6 years in, everything is still a mess. There are a lot of academic papers that have tried to classify various types of speculative attack and in terms of what went wrong or what buffer it is. And I find these interesting to look at, and I ignore them. Because all the academics are trying to do is apply some logic to a problem that exists because no end-to-end logic was applied in the first place whilst building the CPU. So I don't think it falls into any nice set of categories other than the ones we came up with originally. Deferred fault checking, that Meltdown was the archetypal example there. There are some software workarounds, some hardware workarounds, some not being fixed, but this is now an understood problem. It's a very limited problem space. It was extensively analyzed. People know about it. The other big one is access to microarchitectural buffers. That has caused a lot of problems. Intel suffered more than most on that. And these are still being found. Everyone seems to agree they're a bad thing, and typically they're mitigated with new microcode to do more flushing of more buffers and that. The example here, APIC leak, is not a speculative attack, it's an architectural attack, but it demonstrates that even in an era where speculation is a critical safety concern, they still accidentally managed to put in yet another leakage that caused problems to the rollout of Sapphire Rapids, amongst other things. The thing here goes back to what I said earlier. The vendors are learning at the same rate as everyone else. The biggest problem, though, is the predictions, and I include both branch and memory predictions here. We're going to focus on branch more than others. This is where there is a conflict of interest. The vendors can only sell CPUs that top the new benchmark, so everyone cares about getting performance, because if you don't have the top performance, you don't sell your CPUs, and you might as well go and find another job. So selling CPUs is in direct conflict with this final safety requirement, which is why why there is a lot of argument over what can and can't be done about it. This is a perfect example. This is one that has caused a huge amount of effort in Linux, and at some point I need to import it to Zen as well. This is a Skylake Core. For those of you who remember the original Spectre and Meltdown, one of the things that we did was Repelin, software sequence. And there was a caveat on Broadwell hardware that it was safe, but only after you had a microcode update. Broadwell hardware had a chicken bit, and the microcode update went and turned it off, therefore the software sequence was safe. But when the Skylake Core was designed, they designed it without this control bit in it. As a result, Repelin was not safe. There were some large upstream arguments over it. Eventually, RepBleed as a new vulnerability came out, which led to a completely new software technique called call depth tracking. And it took another 6 years for Intel to put the chicken bit back in. That has eventually turned up in Alder Lake, but it took a lot of arguing. From the point of view of security, and I mean here mostly the Zen security team, we have to assume that an attacker can win every time. Because they can. They can repeat forever. They can afford to spend months and months trying to win a fraction of a race. The software techniques need to be deployed perfectly. The hardware controls need to be deployed perfectly. The researchers do notice when we get this wrong, usually in the form of another CVE and another embargo. The hardware interfaces for this, IBRS, it is nominally a common ABI. Both vendors say you write one to this bit and it does stuff for you, but the APIs are completely different. There's the legacy Intel form, which was what they retrofitted in microcode to existing CPUs at the time, and it's different to enhanced IBRS, which is the mitigation that you're supposed to do in new hardware that has new controls of it. AMD decided to make a stronger guarantee, but they suffered some of the problems of the original IBRS microcode. You have to toggle it on a fast path for several generations, and then they introduced Auto IBRS later that lets it toggle automatically. But even Auto IBRS has behavior that depends on whether encrypted VMs are active in the firmware or not. So even if we as the hypervisor are not using encrypted VMs, the behavior of some of our safety primitives changes depending on whether it was active, whether the user enabled it in the firmware or not. Bugs happen, a lot of bugs happen, and there is still areas that are open for research. This is an example of a modern core, and before you all start laughing at me, yes, it's in Harlem. The point is, it mostly fits on the slides, it's reasonably simple, and it's more modern than the stuff you get in academia. The important point to note about a core, really, is that it's just a ring of data around the L2 cache. Ultimately, the performance of your core is trading off the memory accesses for instruction fetches with the memory accesses for data reads and writes. Your core is only useful if you can get the calculation out, and the only way you get the calculation out is ultimately writing it back into memory. So everything inside the core is just an incidental way of making that happen. Also, it doesn't show up terribly well on the projector. I've tried highlighting in purple each thing that is a buffer. And what you can see there is there's basically a buffer between every stage in the pipeline. This is not to scale. The buffers are substantially larger than in some cases, than the units. Each area of the pipeline can stall for complicated reasons. Instruction fetch might stall because it's got to do a TLB walk or satisfy a cache miss. And you don't want the rest of the pipeline going idle whilst you're stalled on an instruction fetch. So there are big, huge buffers between the various components, such that a delay in one area doesn't affect the overall throughput in the other areas. Obviously, you get best performance when all of these are balanced nicely and you're not blocked on one of them. But the point I'm trying to make is that a CPU core is actually just an asynchronous system. You could replace each of those, conceptually replace each of those buffers with a network cable and some network switches, and you've still got the same base behavior. But now you think of it much more of I've got to wait for a while to talk to something else, or wait for a while to get an answer back. And that is genuinely how the cores behave. Okay, we're talking hundreds of clock cycles, not milliseconds, but it takes time to get a signal across a core, which is why there are buffers, there are fast paths, there are signals. It takes a while for a signal to take effect. It may take 4 or 5 clock cycles to get a signal from one end of the pipeline to the other, simply because of physics across the size of the chip. This is my very small attempt at describing the core slightly more simply, and in a way we'll refer back to later. The important thing to understand about CPUs that is different to everything you see in literature is that the branch predictor is first. Traditionally in the literature, it says you go along, you decode an instruction, you figure out it was a branch, and you say, okay, it's a branch, well, where does that branch go to? That's not how computers work, because that has too much latency in it. So instead, the branch predictor is at the front, and it just produces a stream of consciousness. It produces a stream of addresses based on where it thinks the current instruction pointer is and the entire history of everything that has come before. One thing that I frequently get asked is, hey, why don't you just turn off branch prediction? And this is why not. You cannot turn off branch prediction, because if you turn off branch prediction, the CPUs can't fetch instructions these days. It's been like this for a decade. So you simply cannot turn off branch prediction. And that guides a lot of what we do and don't do in terms of the speculative protections. Now, it's worth pointing out that at each step along the pipeline, there are signals that go back. So these I've done in red. The important one is the resteer. Resteer is a signal basically says, go start again from this new address. So you can get a resteer out of decode, where decode comes along and says, well, you predicted that this was a branch, but it's not a branch, therefore something went wrong, and it issues a resteer to the front end. And the front end says, okay, well, I'll stop doing that, I'll pick some new addresses, go and fetch some new bytes. It's more than just the address, it also feeds back metadata. So the decode, for example, sends back a stream saying, this was this type of branch, that was that type of branch, simply to update the branch prediction information with known accurate data. Later in the execute units, you get a resteer. All branches have to execute, just like every other micro-op in the pipeline. And one of the things involved there is checking to see whether the prediction was correct or not. In the case that the prediction was wrong, everything you have fetched, everything you've decoded, and everything you have scheduled behind that branch is wrong, or potentially wrong. So, a resteer is a signal out of an execute unit. This is the speculative resteer, it's the middle red line, that says, hang on, we got to execute, but something has gone wrong. It issues a resteer to the front, and the front starts again from where it thinks it might want to go. There's also a resteer from the retire stage. That's the point at which it's trying to figure out whether the micro-op was correct or not. The resteer at retire basically says, something went completely catastrophically wrong, start again from this instruction pointer, which is flush everything out of the pipeline and start from the current recorded architectural state. That one's very expensive. I've also listed the memory clear in blue. Memory clear, again, it's a side effect of bad memory prediction. It's relevant to an example later, but there are other memory clears and other resteers that happen for other events. Also, because I didn't want to do too many slides, I put a couple of notes here. lfence is the base primitive that we use in the x86 architecture for protecting a lot of speculation. And what an lfence instruction does is hold at dispatch. lfence prevents any new micro-ops entering the execute units until the lfence is the oldest instruction in the pipeline. That is the base primitive. It's why we use it a lot. It's why it gets referenced a lot. I also annotated how Intel and AMD are doing the hardware fixes for Spectre v2. So Intel EIBRS on this side works by tagging the predictions and saying, right, okay, in this mode, I only use predictions I learned in this mode. So it deliberately excludes some information in the branch predictor to try and not let that be controlled by an attacker. AMD do it differently. AMD, wrong button. AMD, again, hold at dispatch. The problem with Intel's model is that you still get a thing called same mode training. If there's a type of attack called a confused deputy attack where you use legitimate code in some other environment to do something you want, and that can include putting bad data into the branch predictor. AMD said we don't want that, so AMD just they don't disable prediction. They say they disable prediction, but you can't turn it off. So instead, when they issue a branch into the pipeline, they just automatically hold there and wait for the speculative resteer to start the pipeline again. It has better security guarantees. It is not as performant as a trade-off there. So, all good speculative presentations need to come with a bad code example. Normally it's a bad code example of Spectre v1. Here I present to you Spectre v1.1, which is a far more interesting example to look at. It's a classic branch problem. But instead of using this to read data, you use this to write data. And notice that if you come in, and index is maybe 10, 11, something like that, you end up overwriting the return address on the stack. Speculatively, but you have updated it you've generated a store that lives in the store queue. And this is hidden in the middle of one of the Intel web pages is a description of how potentially a RET instruction might execute. RET instructions are the hardest instruction to deal with because they are really pernicious in a corner case. The example here says that the if condition is predicted taken, therefore you perform the store, and the store is speculatively out of bounds, but it's fine. You put it in the store buffer, it's not architectural yet, and at some point later, the RET micro-op comes along to check. It gets down to execute, and checking involves reading the top of the stack. It reads the top of the stack, gets a bad store to load forward, at which point the RET micro-op says, oh, my prediction was bad, and it issues a resteer, out of the execute unit to the attacker-controlled address. This is a problem because it's actually an example in the pipeline where the resteer escapes the context in which it was bad. If it hadn't have done that, just deleting the micro-ops would actually have fixed it, as happens with some of the other Spectre 1 defenses. In this case, the bad resteer occurs, the front end goes to the attacker-controlled destination, and can genuinely execute real instructions there whilst the memory unit is still figuring out that it did something very, very badly wrong. Later, it eventually does figure out it went badly wrong, clears absolutely everything in the pipeline, and refetches the ret instruction. This time it comes around and it says, it's a ret instruction. Oh, look, my prediction was good this time. It's important to stress that this is one sequence of events. There are many other orderings of events because this is a big dynamic system. This attempts to step that through on the same diagram. You have the prediction originally for the ret that is a good prediction. Later, a store occurs, step 2, and then the only ordering constraint actually is step 2 and step 3. Step 2, the store has to occur before the ret reads the stack, because that is a constraint, that's a chronological constraint even under speculative execution. Executes bad resteer, the attacker 4A and 4B actually gets real micro-ops through a pipeline, and eventually it gives up restarts from scratch. This demonstrates that the problems from memory predictions are actually substantially worse, or substantially more subtle than problems from branch predictions going wrong. So much so that the memory predictors themselves have inbuilt hysteresis loops to turn themselves off after the processor has decided that the memory predictions aren't necessarily any good. So it's also far harder to deterministically trigger them, which is also why it is an area of research that not many people have looked into. So those are ret instructions. They're problematic because they are used absolutely everywhere. In some cases, with the Repliene gadget, we are deliberately using them to fix a different speculative bug. The Repliene gadget is vulnerable to this attack, but it's sufficiently corner case that people try not to care about it. But it has driven discussion as to what to do to fix this. The example here, the set specification, control flow enforcement, was at version 2, and then Spectre Meltdown hit, and it had some substantial rewrites before version 3. Version 3 came in with a whole load of new speculative guarantees that previously no one had cared about, and both Intel and AMD have done similar things. They have specified which predictors can and can't be used. AMD will not execute the ret instruction if the stack and the shadow stack disagree with each other. So they will hold the ret instruction for a while. Intel went even further. They said that they won't execute whilst there are any pending stores to either of these locations. In both cases, what this means is that the ret instruction waits a little bit longer, and therefore it does not issue the bad resteer that escapes out of the bad execution and back to the front end of the pipeline. Yes, it's been a bit of a deep dive into ret instructions, and ret are the hard instructions, but they're only one of several types of branch. They're one of a very large number of memory accesses, and half an hour really doesn't do this topic justice. But these are the kinds of problems that we're dealing with. These are the kind of problems that the hardware vendors are dealing with. It's worth noting that even within this, mistakes have been made, problems have been patched in microcode. You, for example, do not want to know how many times IBRS was fixed in microcode. You can count it by the number of microcode releases since Spectre. The problems keep on coming, and because there is no deterministic fix, the original major problem between selling CPUs and making them faster means that mistakes are still happening. Mistakes are happening at the hardware level. Mistakes are happening at the software level. We're not perfect. We've had bugs in our speculative fixes. We put out XSAs when we find them. But there are also bugs in analyzing the behaviors of the processors, which is why various researchers keep on coming back and finding new variants of the stuff they already previously disclosed that the hardware vendors thought they had analyzed fully and were done with. So this is a problem that is going to keep on going for the foreseeable future. There isn't really an option. Unless anyone has any bright ideas, I'm sure Intel or AMD would pay big bucks if you can actually solve these problems. One thing I have seen is research from a university in America called Speculative Taint Tracking is the only thing I have ever seen that tries to account for the behavior of speculation inside the pipeline. Unfortunately, people at the hardware vendors look at it and say, maybe, but we're certainly not seeing it in hardware anytime soon at the moment. So yes, in terms of safety, I'm still not confident that we've got safe CPUs. I'm not alone in that view. So on the question of whether you trust two workloads on the same system, I guess that's up to you, but we try our best. We make no guarantees. Okay, actual real questions this time?
Okay, so x86 we've seen here. We've seen those issues on ARM2. What about other architectures newly designed and slowly starting to be supported?
Okay, so the other architectures in the world, PowerPC suffers all of these. PowerPC even suffered L1 terminal fault, which was slightly embarrassing for them. Oh, okay, fine. The problem here is it's caused by high performance designs needing to be a disaggregated system to a certain extent, and you see it in the big designs. Something that's not terribly well known is that Apple iPhones and iPads were fully vulnerable to meltdown. They did an excellent job of technically saying that in their security announcement and and hiding it very well. Recently, there has been an attack, a speculative attack against a RISC-V processor that was running a trusted execution environment as a plain Spectre v1 that just read the key straight out of the hardware trusted enclave, because the people currently building RISC-V processors are looking at it and saying, right, well, we need to do this to go fast, and the problem is the going fast. If you're willing to have a microcontroller that that doesn't do anything out of order, doesn't read ahead, then yes, you can make it secure. But what you can't do is make it secure and also run the kind of software that we run today.
Just one concern I have. You said that we can earn a huge amount of bugs by solving this problem. But on the other hand, how to get so deep into this architecture and whole branch prediction to actually know how to fix it, actually? Because this is kind of some kind of, I think, intellectual property which Intel wouldn't likely to reveal to anyone.
So in a lot of cases, I gave a similar talk to this previously, and I deliberately this time around did not include a layout of what the branch predictors look like, because what the branch predictors look like is mostly described in terms of academia, because academics have a split between the conditional predictors and the indirect predictors as a technique of explaining it to people that don't know branch prediction. That's not how it works. Branch predictors in processors are an amalgamation of stuff. It's got more complicated things like loop predictors. Basically, any high-performance architecture now can figure out what the induction variable of a for loop is and not mispredict on the exit of it, because the branch prediction realizes that the loop ends when this value gets to 0, or when the other way around becomes positive. When you have tracking like that, AMD in some of their marketing slides call their branch predictor various bits of inference engines now, trying to get the AI terminology in. So what the branch predictor actually does bears no relationship to anything I can put on a set of slides or anything that exists in a research paper. At that point, you basically have to trust Intel and AMD to do their analysis right, and as you can see, in the past 5 or so years, they've been perfect at it every single time. The researchers tend to find this by saying, well, if that's not true, what else happens? And they find the else on the side. In terms of understanding at this level, there are some people, but it's really complicated. A lot of it is covered by NDAs. I've got a lot of interesting stories that I definitely cannot tell, that I definitely can't put on slides, simply by having the conversations with the people that build CPUs. At the end of the day, it is a collaborative effort, and so much is proprietary secret. Intel, for example, absolutely hated admitting that the special register buffer existed, but it was necessary in order to explain the security problem and describe what the fixes for it were. Similarly, for microcode assists, they are having to document bits that they kind of considered trade secret in order to first explain the issue well enough to then explain how the fix for it works. So Intel and AMD really don't like publishing this because they see it as publishing some of their super secret source. They do the absolute bare minimum they think they can get away with to not be called out on by security people. But it's a process. No one can come along and magically learn all of this overnight, because apart from anything else, no one is going to be able to see the RTL of both Intel and AMD CPUs to look at it and see whether there's a common issue or not. Okay. Any other questions, or are we definitely getting on for lunchtime? I think we're definitely getting on for lunchtime.